Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here at my virtual classroom. Stepping inside, and thank you so much for joining me alongside this journey as we continue in the Big Ideas Math Integrated Math 2 textbook, where we are now on Chapter 9, Right Triangles and Trigonometry. And we start with Section 9.1 on the Pythagorean Theorem. You may know the Pythagorean Theorem, but there's more to it that I'm sure the book's going to talk about that I've done in the past, and that leads into how we use it for future portions of this chapter itself. And if you haven't done trigonometry before, it's a fun enough ride, at least for me, and what we do with it in IM2 and stuff. Oh yes, get ready to go. This is just the crux of everything moving forward. We're going to start with the lecture portion on this. Check out the PDF if you want to follow along with it. Download it down in the description section below, And also after that, we're going to do the entire problem set. I don't know how many problems. I wrote it before, and it's somewhere in the 40s of a whole problem set. And if you'd like to follow along with that, please do so as well. Let's go ahead and get started. Oscars are behind us, by the way. We're going to learn to use the Pythagorean Theorem, the converse of the Pythagorean Theorem, and to classify triangles based on the Pythagorean Theorem, in a way. Pythagorean triple will be part of our new core vocabulary. I'm glad that they're introducing it here and now, so I don't keep saying, this is how I know what this is. This is how I know what this is. So, yes, Pythagorean triple. Previously, you had to know what a right triangle was, the legs of a right triangle, and a hypotenuse of a right triangle. So I'll just say that right now. Here's a leg, there's a leg, here's the hypotenuse. The legs are the two sides of the triangle that make up the right angle. And the hypotenuse is the side opposite the right triangle in a right triangle. Using the Pythagorean Theorem. Oh, we get to read history. One of the most famous theorems in mathematics is the Pythagorean Theorem, named for the ancient Greek mathematician Pythagoras. This theorem describes the relationship between the side lengths of a right triangle. I gotta sneeze. I'm gonna pause before this happens. Excuse me. Okay. Pythagorean Theorem. In a right triangle, the square of the length of the hypotenuse is equal to the sum of the squares of the lengths of the legs. That says a lot. The way that we say it is a squared plus b squared equals c squared. Or the way that they say c squared equals a squared plus b squared. A and b are your two leg lengths, and c is your hypotenuse. Now, I've been using Pythagorean Theorem all the time, every time we've used distance formula. So if you followed along with any time that I've done it in old textbook things, you've used the distance formula and said, I'm going to use Pythagorean Theorem. You know Pythagorean Theorem, right? It's basically understood that you know it by now. That doesn't mean you're supposed to. I'm saying that in my video stuff, I'm just realizing this. I use this all the time with you guys, so hopefully this is going to be pretty easy practice. And I've been simplifying radicals and things like that as well. Looks like there's a proof that we get to do or explore it. I might do the proof with my students as well, but yeah, we get to look at it here. A Pythagorean triple, cool, they're introducing it right now, is a set of three positive integers a, b, and c that satisfy the equation a squared plus b squared equals c squared. The four most common Pythagorean triples that you see are right here. Basically, 3 squared plus 4 squared is 5 squared. 5 squared plus 12 squared is 13 squared. 8 squared, like that. That's what they're telling you. And these are all made up of integers. It's not true that you can use integers for any set. 6 squared plus 9 squared won't give you an integer out. You know what I mean? So these can be the leg lengths of right triangles that are all integers. Now these are unique ones in and of themselves right here. What you see below them are integer multiples of those values. Like if I double 3, 4, and 5, similar triangles. If I gave a scale factor of 2 and a scale factor of 3 and a scale factor of x, basically. If you change the scale factor to 3x, 2, 3x, 2, 3x, right here, these are Pythagorean triples, but these are 4 classically known ones. Why might you want to know them? Because they show up a lot, because books and websites and teachers like to come up with problems that will give you clean numbers sometimes. And so these are very common ones to know. So when I say, I know this length is going to be 15, because I know this is in a 3 to 4 to 5 relationship in that. The most common, and I'll just read there from here on out. The most common Pythagorean triples are in bold. The other triples are the result of multiplying each integer in a bold-faced triple by the same factor. So 5, 12, 13 times 3 gives you those, things like that. All right, using the Pythagorean Theorem, find the value of x, then tell whether the side lengths form a Pythagorean triple. Well, I can tell you that's going to be 13 because it's a 5, 12, 13 triangle. So c squared is a squared plus b squared. 5 squared is 25. 12 squared is 144. 25 plus 44 is 169. Square root of that is 13. Now, normally we'd go from here to here and we'd say x is plus or minus 13, right? But distance can't be negative. Distance must be positive, so we're going to leave it as such. The value of x is 13. Because the side lengths 5, 12, and 13 are integers, they form a Pythagorean triple. So to form a Pythagorean triple, you need all integer values. All right, let me move myself. All right. Using the Pythagorean theorem, once again, find the value of x, tell whether it's a Pythagorean triple. I can tell you this will not be, just by knowing that's not part of one. 7 squared plus an unknown squared equals 14 squared. See, I don't just do 7 squared plus 14 squared is x squared. And a lot of people will do that in a problem like this. Not because it's the first two numbers that you see, but because you see x as a slanted value, or, a slant, and you think of hypotenuse as a slanted thing. But the right angle is right here. The right angle is up there. And x is just one of the legs. So x and 7 are the legs, 14 is the hypotenuse. Now, you get the square root of 147, which simplifies to 7 root 3. 49 is a perfect square in there, perfect square factor. 7 root 3 is not an integer. Just because 7 and 3 are integers doesn't mean 7 root 3 is. 7 times the square root of 3 is just a value. I don't know what it is. It's somewhere. It's a little more than 12. It's a little more than 12. It's not a Pythagorean triple. All right, solving a real-life problem. Probably a classic things we're going to see in a lot of word problems for these. The skyscrapers are shown are connected by a skywalk with support beams. So here's the skywalk of the two skyscrapers. And here are support beams for it. Use the Pythagorean theorem to approximate the length of each support beam. So these are each 47.57 meters from the skywalk to the bottom of the support beam here. And then 23.26 meters goes all the way across here. Oh, each of these are 23.26 meters. Okay. So 23.26 here, 47.57 here, and this unknown length here. So we got to do this squared plus this squared equals that squared. And then you take the square root of the value you get and round to the nearest hundredth is 52.95. So I have to get my calculator out for these problems, it looks like. I see Jimmy Kimmel in the background. I have to get my calculator out for some of these problems that we're going to do to approximate them after. All right, some examples for us to do. I'm going to leave them. We're going to do the problem set later. Using the converse says that if you have in a triangle, if a squared plus b squared equals c squared, then it is a right triangle. So this is one of those theorems where the converse is also true. So, we say in right triangles a squared plus b squared equals c squared, but if in a triangle that's not known to be a right triangle that you have that, then it is. And that's important for when we classify triangles of other types as well. So, are each of these right triangles? We got to figure out, is 7 squared plus 8 squared equals the square root of 113 squared. Now, how did I know that I had to choose 7 and 8 here? Is it because this one looks like a right angle? Maybe, but 7 and 8 are also smaller side lengths than root 113. I know root 113 is more than 10 because root 100 is 10. So I got to check those. 7 squared plus 8 squared is 49 plus 64, which is 113. Root 113 squared is 113. Because they both equal each other there, this is a right triangle. Yes, indeed. We can try 15 squared plus 36 squared equals 4 root 95. I'm honestly just going based off the visual. I'm going to assume these are the ones that we're going to test it for. So I'll let them calculate it for the sake of the example. And look how close these get. 4 squared is 16, root 95 squared is 95. Multiply those, you get 1520. Add these together, you get 1521. It's not a right triangle. It might as well be. Like, it might be 89.9 degrees or whatever, but it's not a right triangle. Okay, let's classify triangles now. The converse of the Pythagorean theorem may determine whether or not you have a right triangle, but if it's not a right triangle, that means it's another kind. If it's not a right triangle, it's either acute or obtuse, and you can determine which one it is. If a squared plus b squared is greater than c squared, and make no, see, I don't like that they write c squared, da-da-da. I like to use the a, b, then c. If a squared plus b squared is greater than c squared, you're looking at an acute triangle. That those legs, they're not legs anymore, but what would be legs in a right triangle have now dominated over that hypotenuse, that they are overwhelmingly larger than, not overwhelming, but they're larger than c squared when added together, when squared and added together like that. And when they're less than c squared, then that c is dominating more so in the triangle, and then this is an obtuse triangle then, if a squared plus b squared is less than c squared there. So we can check out some examples. Are our triangles going to be acute, obtuse, or right based on this? They can still be right if it equals. So we'll see. Oh, and also, and I was going to bring this up, but I didn't know if they were, so I didn't. So they're going to here. Use the triangle inequality theorem to verify the segments form a triangle to begin with. You have to make sure that when you do these, that they're even allowed to make a triangle. You remember that one? That a plus b itself has to be greater than c. I'm not talking about Pythagorean theorem. I'm talking about the lengths of any two sides of a triangle added together have to be greater than the third side. Not equal to. They have to be greater than. So 4.3 plus 5.2 is more than 6.1. Therefore, this can make a triangle. I don't need to bother testing with some other ones like they are. If 6.1 is the longest side, there's no bother. It needs to test that. So they at least form a triangle. Now, what kind of triangle? Let's try the two shorter sides, 4.3 and 5.2, square them, add them together, and see if they are more than, less than, or equal to 6.1 squared. They apparently are more than 6.1 squared. A squared plus b squared is more than c squared, and if that's true, we have an acute triangle. And that's what we have here. Okay, and that is the last example. So I'm going to jump in, guys, to the problem set, starting with the vocabulary and core concept check, and then we'll do the official numbers 3 through 40-something. What is a Pythagorean triple? It is a series. It is 3 integer values that can be used to form a right triangle. Now, there are special ones that we use, if you remember them. It's going to take a while to remember them or to practice enough things until you know them. But 3, 4, 5, 5, 12, 13, 8, 15, 17, 7, 24, 25, and any other similar triangles that have integer scale factors there. Same words, different question. Number 2, which is different? Find both answers. I know this is a 3, 4, 5 triangle, by the way. I'm going to use that just in case. Find the length of the longest side. Well, we got to do that here. Well, I'll just write an A there. Find the length of the hypotenuse. That's also going to be the longest side of any right triangle. Find the length of the longest leg. No. 4 is the longest leg. The legs are the ones that make up the right angles. That one's different. Find the length of the side opposite the right angle. That would also be an A. And by the way, that answer would be 5, as it would be a 3, 4, 5 right triangle. So all these are the same. This one is different. Okay, guys, we are going to jump into the problem set, and we're getting applause for different Oscar things. Go Oppenheimer. So let's go ahead and see what's going on with this problem set. We are going to do numbers 3 through, let me check before I flip through, 3 to 43. Okay. Now I will have to pop up the calculator at some point, I'm sure. For now, I'm going to see how much I can do without it until like word problems at the very latest. Okay. So let's go ahead and start with numbers 3 through 6, where we find the value of x, then tell whether the side lengths form a Pythagorean triple. So they form a Pythagorean triple if the x that we find is an integer alongside the other two that are already integers. I can tell you yes, no off the bat just by looking at the numbers and no. Number 3 is going to be a no. Now, for these ones, it's already drawn, so I'll go ahead and just do the setup for my own sake. 7 squared plus 11 squared equals x squared. X is the hypotenuse. 7 squared is 49. 11 squared is 121. 49 plus 121 is 170. Now, x is the square root of 170. 170 is 2 times 85. 85 is 17 times 5. I don't believe any of those can simplify, so I'll leave it like that. I'm not going to round it. Not a Pythagorean triple. When I answer yes or no right here, I'm saying whether or not it's a Pythagorean triple. No, this one's not. Now again, how did I know beforehand? Because I know the Pythagorean triples. I'm sorry, I don't know if I'll know all of them. I'll know the ones off the multiples of the 4 common ones. If there are other ones that are bound to be, and I don't actually know them. So some of these might be. 7 and 11 were too small to know that they weren't for sure. Number 4, I believe not. Wait, 850. Yes, it is. This one's going to be the Pythagorean triple. Okay. So here we have 16 squared plus 30 squared equals x squared. This answer is going to be 34, by the way. 16 squared is 256. What happened to my calligraphy here? That marker looks different. Give me 1 second. I don't know how to change. Okay, I'm just going to change it now. And you might even like that look of the writing more. I'm just not as used to it. Plus 900 equals x squared. And that would become 1156. Now, I'm glad that I know it's a Pythagorean triple because I don't know this off the top of my head, the square root of 1156, but I know that the answer is going to be 34. So I'm just going to go ahead and write that. That must be its square root. Is it a Pythagorean triple? Yes. How come? This is an integer alongside 16, 30, and 34, which, by the way, it's a part of the 8, 15, 17 Pythagorean triple set. If you double all these lengths, that's kind of why I know it. Number 5. This could be a Pythagorean triple, and I wouldn't be aware, so I don't know. I might have to whip out the calculator for this one. 9 squared plus 40 squared equals some x squared, and these are all hypotenuses. 9 squared is 81, 4 squared is 1681. If it is, it's probably going to be 41. What did I just do? This should say 1600 and then 1681. X squared equals 1681. The square root of 16, I gotta do the calculator now. Actually, I'm just gonna try 41 squared and see what I get. 41 squared, I get 1681. So x is 41. This is a Pythagorean triple. So yes, Pythagorean triple. It is of the 9, 40, 41 set, of which I didn't know existed. Yeah, there it is. And number 6. 6, I know this one's not one. 4, 6, and some unknown. Let's figure out what this is. 4 squared plus 6 squared equals x squared. 4 squared is 16, 6 squared is 36, and x squared is 52. So x is the square root of 52. Now, 52 is 4 times 13. So the square root of 4 is 2, and the square root of 13 stays as such. So we'll leave it like that, 2 root 13 as we simplify it. No, not a Pythagorean triple. 2 root 13 is not an integer. Okay, let's move forward and look at numbers 7 through 10, where we find the value of x, then tell whether they form a Pythagorean triple. No change from the last problems, except, based on the first two that I see, it looks like we are now instead using legs that are unknown on these. So I'll write them as x squared plus my other leg squared equals the thing squared. So now x is not the hypotenuse. This answer will be 15. This is a 8, 15, 17 Pythagorean triple. So x squared plus 64 is 289. Subtract 64 from both sides, x squared is 225. Take the square root of both sides, x is 15. Yes, this is a Pythagorean triple. This, once again, is part of the 8, 15, 17 Pythagorean triple crowd. Like I said, it helps to know them because of how much they pop up, especially in a section devoted to them. Or a chapter that will devote to them. Number 8. I don't think it's Pythagorean triple. Number 8, x squared plus 9 squared is 24 squared. Whoops. X squared plus 81 equals 576. I mean, here's the thing. You've probably done Pythagorean theorem before, so hopefully this isn't anything too new. X squared equals 495. I'm not that bad at math, am I? Is right? And x is the square root of 495. Now, if you divide it by 5, you get 5 and 99. 99, 9's a perfect square. So 3 root 55. 3 root 55, I think it's 9 times 55. Yeah, 3 root 55. Pythagorean triple? No. Not a Pythagorean triple. Okay, let's keep moving forward. Numbers 9 and 10. Whoops, I just undid something. Numbers 9 and 10. Number 9. This answer is going to be 14. So x squared plus 48 squared equals 50 squared. If you think I squared these things to answer that, I don't even know what 48 squared is. I tried to get it. 49, 2404. Am I even close? 48 squared. 2304. Darn. X squared plus 2304 equals 2500. Oh, that's right. X squared equals 196, so x is the square root of 196, which is exactly 14. Yes. How did I know? This is part of the 7, 24, 25 Pythagorean triple. You double all of these and you get those values. 25 doubled is 50, 24 doubled is 48. 7 doubled is 14. That's the one that I found. Number 10. Not a Pythagorean triple. I don't know what it is. We'll figure it out together. X squared plus 7 squared equals 9 squared. That's x squared plus 49 equals 81. Subtract 49 from both sides. You get x squared equals 32. Take the square root of both sides. You get x equals square root of 32, which is 16 times 2, which the square root of 16 is 4. So you get 4 root 2, not a Pythagorean triple. Okay, in 11 and 12, describe and correct the error in using Pythagorean theorem. This probably isn't a common thing that people do specifically, but there are things off of this that people will make a mistake of. So I'm identifying the mistake already. They are assuming that a squared plus b squared is the same thing as taking a plus b and then squaring it, as if to say 31. 7 squared plus 24 squared is 31 squared. No. The thing that people make a mistake off of this with is assuming that you could just take the square root of both sides and be good with it. That if a squared plus b squared equals c squared, then a plus b equals c. First of all, we should know that's not true by the triangle inequality theorem. Second of all, if we could do that, then why don't we do that all the time? Why don't we just say a plus b equals c? What are you doing, Pythagoras? Because they're not the same thing. And we're going to show they're not the same thing. The answer is not going to be 31 here. They falsely assumed that a squared, I'll fix this in a second, a squared plus b squared is the same as a plus b quantity squared. All right, let's go to fix that. Boom, and boom. When it is not. So that's the error. Let's fix it. Let's say 7 squared plus 24 squared equals x squared. And by the way, this answer should be 25. It's a 7, 24, 25 Pythagorean triple. This is 49 plus 576, which is 625. And the square root of 625 is 25. So that corrects the error. That is the correct answer to this thing, not 31. Hopefully we learned off this as well. All right, number 12. I'm going to assume that they made x the hypotenuse. So let's see. Because I see it as a leg. So number 12, So number 12, they have 10 squared plus 26 squared equals x squared. They treated x as the hypotenuse. They treated x as the hypotenuse when really it is one of the legs and should be shorter than the hypotenuse. And remember, our hypotenuse in this case, hypotenuse is 26. So less than 26. Okay. Yeah, your hypotenuse should be your longest side here, but if you treat all the other ones like that. And maybe people wouldn't make a mistake in this problem as much as another one, like I said, when it looks like x is slanted. And they say, it looks slanted, it must be a hypotenuse. No. So the setup is incorrect here. It's not 10 squared plus 26 squared is x squared. It's, x squared plus 10 squared equals 26 squared. Now, they helped me out here. I didn't know 26 squared was 676. I hope that's not one of their mistakes. I assume it's not. Actually, I know what this answer is going to be. It's going to be 24. So this 676. So x squared equals 576 when you subtract. So take the square root of both sides, you get 24. This is a Pythagorean triple of the 5, 12, 13 set. Remember, if you double these, you get 10, 24, 26. Well, these are the ones that we already had, and this is the one that we just found. So doubling all those gets that. Hey, we already learned triangle similarity off that. Okay. excuse me. Let's keep moving forward. Number 13. A word problem, something where I probably have to use the calculator. Modeling with mathematics. The fire escape forms a right triangle as shown. Use the Pythagorean theorem to approximate the distance between the two platforms. So solve for x here. They show you a right triangle. Hopefully you can see the entire visual. I gotta find x. No harm. We're gonna round. Let's round to the nearest tenth. These are single decimal values. They don't ask us what to round to. I'm assuming it's not going to be exact. And our answer needs to be in feet. X squared plus 8.9 squared equals 16.7 squared, none of which I know what these things are. 8.9 squared, close to 81, 79.21. So x squared plus 79.21 equals, and 16.7 squared. Sorry, I'm not showing this. This is it's just squaring numbers. 278.89. Let's subtract 79. I'm going to use my calculator. 79.21 from both sides here. And I get 199.68. That's not the answer. We have to take the square root of both sides. And I take the square root here. And I'm getting 14.1308, whatever. So I'll say it's about 14.1 feet. And that's the approximation for myself on that problem. Okay. All right. All right. Number 14. Modeling with mathematics. The backboard of the basketball hoop forms a right triangle with the supporting rods as shown. Use the Pythagorean theorem to approximate the distance between the rods where they meet the backboard. Once again, they're giving context to something, but you're still using Pythagorean theorem to make it happen. Let's do it. We have x squared plus 9.8 squared equals 13.4 squared. Okay. Again, don't know my numbers. Let's 9.8 squared is 96.04. Equals, and 13.04 squared. Oh, 0.4. Excuse me, 13.4 squared. 179.56. Subtract that. Let me see if I can do that in my head. 83.52. I need to write it first. 83.52. Let's see if that was actually correct. Minus 96.04. Yes. This is, and I'm taking the square root of both sides. I'm getting 9.138. So I'm going to say about 9.1. 9.1 inches. Yeah. You know, there are some problem types that I sometimes have qualms with doing in video form. Among them are sometimes graphs, proofs, construction, and ones where I have to use the calculator a lot. Because I feel like it's stuff that I could pause for in the video's sake and something you can do on your own for those ones. For graphing, it's like, I have to construct this thing and whatever. The construction, I don't mind. I don't marry myself to construction, but, you know, using the tool on here and just proofs are a lot. We're going to have to prove Pythagorean theorem, right? They never proved it for us. We're going to have to prove it. I'm aware of the proof. I haven't proved the converse, but we'll figure it out. In exercises 15 to 20, tell whether the triangle is a right triangle. So our test is to see if a squared plus b squared is c squared. I'm going to go for the what appears to make a right angle. I'm not saying it does, or also the two shortest sides in the test. Does 65 squared plus 72 squared equal 97 squared is the question. I don't know the answer to that. It could be. And let's go ahead and find out. I'm just going to go straight into it, guys. 65 squared plus 72 squared. And I'm getting 9409. Does it equal 97 squared? It actually has a chance. 97 squared. Yes, it does. 9409. Is this a right triangle of these three side lengths? Yes. Is it a right triangle? Yes. So that's what let me write it over here. Yes. So right triangle is what I'm answering there. Number 16. 23 is the longest side. That would ideally be the hypotenuse. We'll see if it actually is the case. I was going to say I'm pessimistic about that, but actually it's possible because that would end in a 4 and that would end in a 6. 4 plus 6 might give you an integer. So it's possible. We'll see. Does it equal? 21.2 squared. Oh, 0.44. Never mind. Maybe not. 11.4 squared. Probably not, because this is 579.4. Being a decimal means probably not. 23 squared is 529. 529. I hope I didn't type anything wrong, but I don't think so. And that is not the case here. No, these do not make a right triangle. Now, they didn't ask what kind of triangle it is if I want to speak ahead of this, because this is greater than that. This will be an acute triangle. Number 17. We have 14, 10, and 4 root 19. Well, which is the longest? The one that looks like the right angle is right there. I don't know 4 root 19 off the top of my head, but I'm going to venture a guess that it is the longest length among these because reasons. 14 squared plus 10 squared, does it equal 4 root 19? Quantity squared is the question. Assuming, again, that's the longest. It should be. 14 squared is 196. 10 squared is 100. I'll try this without the calculator. 4 squared is 16 times root 19 squared, which is 19. And 16 times 19, 256 plus 48, is 304. This is 296. This is 304. Not the same, close, but not. Hypotenuse is bigger, which would make it not a right triangle, but an obtuse triangle. Again, not a part of the set, but I can say it anyway. Ha 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 ha. This one looks like it will be. Number 18. It looks like 5 and 1 are my shortest sides. Now, root 26 is a little more than root 25, which is 5, which makes sense that that would be the longest side. So 5 squared plus 1 squared, does it equal root 26 squared? You betcha. Check this out. 25 plus 1 equals root 26 squared is 26. 26 equals 26. That totally checks out. Yes. Right triangle. Number 19. I don't know. We'll figure it out. 2 squared plus 6 squared. Does that equal 3 root 5 squared? 2 squared is 4. 6 squared is 36. 4 plus 36 is 40. And 3 squared is 9. 5 squared is 20. Root 5 squared is 5. 9 times 5. Let me write this. It's just 4 plus 36. 9 times 5 is 45. So we got 40 over here. Let me put question, and no. 40 does not equal 45. No, these are not a right triangle. Hypotenuse is bigger than the sum, or, the square of the hypotenuse is bigger than the sum of the squares of your legs. Therefore, it's actually an obtuse triangle. And then number 20, we have big numbers again for which the calculator will be of great assistance. So 89 the longest side. Let's check and see if 39 squared plus 80 squared equals 89 squared. 39 squared, it's probably something I could come up with, but I'm busy. 1521 plus 80 squared, that's 6,400. And we get 7921. 7921 for those together. Let's check 89 squared. 7921. So they are the same. A Pythagorean triple. Yes. Yes, they are. Okay. Let's keep going. Verify that the segment lengths form a triangle. Is it acute, right, or obtuse? Now, they say verify they are as if they all will be, and it's possible that they will be. If they're not, we shouldn't keep moving forward and keep talking about the triangle. So 10, 11, and 14. I copied down the problem if it's not the image. 10 plus 11, is it greater than 14? Yes, because 21 is greater than 14. So it does form a triangle. Now let's see what kind of triangle this will be. We got to check and see how 10 squared plus 11 squared compares to 14 squared. And I don't know how they actually put it. I'm just going to put a box with a question mark until we figure out what it is. 10 squared is 100. 11 squared is 121. How does it compare to that 196? Well, this is 221. And 221 is greater than 196. Now, the sum of the squares of the legs, not really legs anymore, are greater than 196, not equal to. If they're greater than, the A and the B are devouring the C. This is an acute triangle, not a right triangle, but an acute triangle. Number 22. 6, 8, and 10. I can tell you everything about this thing right now. It's a 3, 4, 5 right triangle. 6, 8, and 10. Is 6 plus 8 greater than 10? Yep, that's 14. It is greater than 10. So we have a triangle. Let's see if 6 squared plus 8 squared is greater than, less than, or equal to 10. Squared, I should say. 36, 64, 100, and that's 100. 100 equals 100. A squared plus b squared equals c squared. Only true in right triangles, as the converse theorem would state. Number 23. 12, 16, and 20. Also a 3, 4, 5 triangle. Actually, this was also a 3, 4, 5 triangle. So, not much diversity. 12, 16, and 20. Is 12 plus 16 greater than 20? 12 plus 16 is 28. 28 is greater than 20. It forms a triangle. What kind of triangle? We'll do 12 squared plus 16 squared and see how it compares to 20 squared. That's 144 plus 256. And that's 400. 144 plus 256 is also 400. And 400 equals 400. We once again are really practicing this Pythagorean theorem with right triangles. It is a right triangle. Number 24. 15, 20, and 26. Not a Pythagorean triple as far as I'm concerned. So 15, 20, and 26. Let's check and see if 15 plus 20 is greater than 26. 35. That's greater than 26. All good. Let's now try 15 squared plus 20 squared and compare that to 26 squared. That's 225 plus 400. 26 squared. I don't know. I know 25 squared is 625. Did we just see 26 squared a second ago? 676? We might have. I think we did. 676. And this becomes 625 on this side, which would be part of the 3, 4, 5 playing thing. It'd actually be 15, 20, and 25 that would work, not this one. This is less than 676. 676 being C value, the C squared. So C is dominating A and B in such a way that when you square it, it's bigger than the sum of the others. That occurs in obtuse triangles, such as that one. Number 25, decimal values for which I will not know the answer for the part, probably acute. But 5.3, 6.7, and 7.8. First of all, 5.3 plus 6.7. Oh, is it greater than 7.8? Well, here you get 12. 12 is greater than 7.8. It's a triangle. Let's move forward. 5.3 squared plus 6.7 squared. Check it against 7.8 squared. And let me do kind of fast calculations now that I have to use the calculator. 5.3 squared, 6.7 squared. I get, when added together, 72.98. And on this side, 7.8 squared, much smaller number because it'll be less than 64, 60.84. This is as acute as it gets. This is greater than, this is an acute triangle because the a squared plus b squared is greater than c squared. Number 26. Ooh, this is close to pushing the bounds of not being a triangle, which is something that would be indicative of an obtuse triangle. 4.1, 8.2, and 12.2. So 4.1 plus 8.2, is it greater than 12.2? Barely. It's 12.3. Still makes a triangle, but by the skin of its teeth, maybe something like this, like that, which means this is probably a very obtuse angle here. So what we're going to notice on this is c squared really being greater than a squared plus b squared, basically. So let's see how that pans out. 4.1 squared plus 8.2 squared. How will it compare to this 12.2 squared? This will just trounce it. So 4.1 squared is 16.81 plus 12.2. Oh, 8.2. Excuse me. 8.2 squared. Add those together, you get 84.05. Now on the other side, 12.2 squared. It's going to be around 150 or more. Whoops, I just did 12 squared. 12.2 squared. 148.84. I was close. 148.84. This is significantly greater on the c squared side. That'll make for an obtuse triangle, like I kind of mentioned before. There you go. Two more in this section. Number 27. 24, 30, and 6 times the square root of 43. I'm assuming that last one is the longest, as they've kind of grown in size each time. 24, 30, and 6 root 43. It very well could be a right triangle, and I'd have no idea. Let's see if 24 plus 30 is greater than the square root 6 root 43. Now that's, I don't know what 6 root 43 is. 24 times 30, or plus 30, is 54. 6 root 43, let me compute that. 6 root 43 times 43 square root. 39.34, etc. 34, etc. It is greater than on that side, 1 plus the other greater than the third. Now that is the longest side. 39.34 is greater than 24 and 30. But these added together is greater than, which is what you want in a triangle. Let's try 24 squared plus 30 squared and compare that, unknowingly, to 6 root 43 squared. 24 squared, 576. 30 squared, 900. 6 squared is 36. Root 43 squared is 43. And 36 times 43 is 1548. These two added together is 1476. Good year, good year. 1548, that still wins. Over here on this side, c squared, that's an obtuse triangle. A squared plus b squared is less than c squared. An obtuse triangle comes out. And lastly, number 28. We have 10, 15, and 5 root 13. 10 plus 15, is it greater than 5 root 13? Let's find out. 25. 5 root 13. I'm kind of hoping one's not so I can do less work. 5 times 13 square root is 18.027, so I'll put 18.03. It's bigger than, that's what you want out of this thing for a triangle's sake. Let's try 10 squared plus 15 squared now and compare it to 5 root 13 quantity squared. That's 100 plus 225. And this is 25 times 13. 25 times 12 is 325. So 325 and 325, they are both the same. That is indicative of a right triangle, which this one is. Okay, number 29, modeling with mathematics again. In baseball, the lengths of the paths between, I do this a lot, between consecutive bases are 90 feet, and the paths form right angles. The player on first base tries to steal second base. How far does the ball need to travel from home plate to second base to get the player out? I said I do this a lot. I coach softball, and I have to explain this one out loud. There are a lot of things I have to explain out loud mathematically. I'm like, this is how I know this, blah, blah, blah. The throw for softball, because there's 60-foot bases, it's like if this is the diamond, these are the bases, 60 feet. What they're saying, by the way, is this makes a right angle. And I know this isn't the baseball one yet. Whatever. This throw is about, right there, 85 feet. It's not exact, but it's about 85 feet in softball. In baseball, I don't remember, probably close to the 120 mark. Probably a little bit less, but we'll find out. So in baseball, the lengths of the paths, I should probably just bring that out again. Let's do this thing right here. It's never a perfect diamond, but oh well. Here's where the catchers throw from first base and second base and third. So this is 90 feet. I don't know why I had to look. This is 90 feet, 90 feet, And we have to find out the unknown x there, basically. I don't need this side of it. I'm looking at this as a right triangle right here, 90, 90, and x. We haven't learned similar special right triangles yet, so I would have another way of doing this a lot faster after this. But 90 squared plus 90 squared equals x squared. That's 2 8100ths. And that will be 16200. So x is approximately, how big? The square root of 16200 is 127. Oh, it's more than 120. 127 point, let's do 2 decimals, 28 feet. That's me using my calculator at the end. Okay, and that's how far the catcher has to throw it. Number 30. Reasoning. You are making a canvas frame for a painting using stretcher bars. The rectangular painting will be 10 inches long and 8 inches wide. Using a ruler, how can you be certain that the corners of the frame are 90 degrees? So with this thing here, you're making a canvas frame for painting. You're using stretcher bars. 10 inches long, 8 inches wide. Using a ruler. So what I need to do is, like, again, we're making the frame. What we want, and I know I'm building a rectangle early on because that's the intent of this thing, but that doesn't necessarily mean that that's what it's going to be. So 10 inches, 8 inches, what we want to do is make sure that we have a right angle here by figuring out whether this thing satisfies some sort of Pythagorean triple, that 10 squared plus 8 squared equals x squared. It says, how can you be certain? It doesn't ask what it is. You need to know. You need to know the diagonal. Well, actually, no. I do need to know how long the diagonal is. No, the diagonal is not x inches long, but I'm going to figure out what that thing is there. So let me give myself some room, do the work, and then answer that exactly. So 8 squared, not a Pythagorean triple, by the way, plus 10 squared equals x squared. 64 plus 100, which is 164. Now, this isn't exact. Let's put it the exact version. Root 164, which is 4 times 41, so 2 root 41. See, if I approximate it, then it won't be exactly a right. Won't be exactly a right angle, a right triangle. 2 root 41 inches. If I wanted to give a version that was like, you know, around 12.8, like that, then it will make a right triangle there. Okay, number 31. In 31 to 34, find the area of the isosceles triangle. Now, an isosceles triangle has equal side lengths. So that shows here 1717, 2020, 1010, and 5050. Now, the area of a triangle itself is 1/2. Let me do that again. The area of a triangle itself is 1/2 base times height. Base being one of the side lengths, you know, it could be 16, it could be one of the 17s. But the height has to be perpendicular to the base you're using. So the base is going to be the bottom one in this case, and the height is this unknown. I will obtain the height in these problems by taking, for example, half, and an isosceles triangle's altitude divides these parts in half. So I can make this 8, and then the other guy would also be 8. Now, for the sake of this problem here, I'll take what we have over there and note that this is an 8, 15, 17 Pythagorean triple. You have to recognize that at some point they want you to know your Pythagorean triples. So h is 15 meters, especially because this isn't the answer to the question. We still have more to do. So if I see a Pythagorean triple, I'm using it. I hope you know that. So the area of this triangle here is going to be 1/2 base 16. Now we're using the whole base, the whole bottom, times the height, because they want the area, right? Times the height 15. Half of 16 is 8, and 8 times 15 is 120. And that's square meters. Let me fix that. So that's number 31. Number 32, listen, none of these are going to change what we do. On number 32, 16 is the value that goes here, 16 feet. Now I have 16 here, an unknown here, and 20 there. I believe h will be 12. Another Pythagorean triple. Now, how do I know that? On this set, for the h, let me draw it this time. H, 16, and 20. This is in a 3, 4, 5 Pythagorean triple, where 16 is 4 times 4, and 20 is 5 times 4, and 3 times 4 is 12. This is the value we're getting for h. 12 feet. Again, without Pythagorean theorem, knowing my Pythagorean triple, and I hope the other ones follow suit. So now the area of this triangle is 1/2. The whole base is 32 times the height of 12. However, just like last time, half of 32 is 16. I can use that, and 16 times 12 is 192 square feet. Number 33. Number 33, divide 12 in half to get 6. And again, the reason I'm doing this is so I can use Pythagorean theorem to find this hypotenuse, because here's where a right angle is made with the altitude. So 6, and yeah, this is another 3, 4, 5 triangle. In a 3, 4, 5 triangle, you can have 6, 8, 10 if you double everything. We know the 6, we know the 10. We need to discover 8. That is the height. This is 8 centimeters. And we keep going from there. The area of this triangle is 1/2 that original base of 12 times the new height of 8. Half of 12 is 6, and 6 times 8 is 48. We get 48 square centimeters. Lastly, number 34. We have, these are all Pythagorean triples, which is nice. 28 divides into 2 to get 14 meters. So on number 34, that 14 with the h and the 50, guys, it's representative of 7, 24, 25 Pythagorean triple. 7 doubled is the 14 you're looking at. 50 is from doubling 25. So the 24 doubled is 48. So without Pythagorean theorem, going straight into it, your height is 48 meters. So area of this triangle is 1/2 base times height. I think I want to use the calculator regardless here, but we'll do half of, let's do half of 48. Half of 48 is 24, and 28 times 24 is, anybody? I have no idea. I think it's 2536. I didn't say that right. 336. 336. I was thinking in the thousands, and I added 96 to 2400 instead of 240. 24 times 28. What did I do? 24 times 28. 672. Where was I going with my numbers? Oh, I was doing 24 times 10. I got to use a calculator. 672. Shh. I was multiplying something wrong, basically. We're all good. We're all good. All right. Number 35. Said I didn't like using the calculator. This is where problems are probably going to get a little bit longer, though. Justify the distance formula using the Pythagorean theorem. You know what? I do that all the time. I don't know if I justify it, but I use Pythagorean theorem instead of distance formula all the time. See, I'm not a fan of using distance formula if Pythagorean theorem will do. So here's going to be my justification. I need to find the distance between 2 points. The distance d between 2 points on a graph, x1, y1, and x2, y2. I need to find the distance between those x's and the distance between those y's. This x distance is horizontal, y distance is vertical. Therefore, this is a right angle that we're dealing with here. The distance between my x's, x1, remember x1 is like this part right here, and x2, is by taking my x2 and subtracting x1. x2 minus x1. The y2, would be this guy. The y1 would be this guy. And these are arbitrary values. Doesn't matter what they are. Distance can be positive. Distance has to be positive. But distance, you can subtract one or the other. But this subtraction is y2 minus y1. Just take one minus the other. There it is. Now, in this right triangle, we have this. We're very familiar with a squared plus b squared equals c squared. So there's a way of me saying a squared plus b squared equals c squared. Now, I kind of feel bad that I was using Pythagorean theorem before this in the book. It was one of those things where I assume they don't reteach it later and say, like, this is your first time using it. And how many times might have I been using Pythagorean theorem without you understanding what it was? I don't know, but I hope you picked up on it over time. So d is the square root of all this. So as far as justifying it, this is where the formula comes from. This is me telling you that distance formula is Pythagorean theorem. I've told you before, I've shown you why a lot of different ways, but here you can see I made the distance formula out of using Pythagorean theorem of the right triangle in the set that you have. All right, number 36 is a how do you see it question. How do you know angle C is a right angle? Well, because I see it. That's how I see it. I see it that way. Angle C is a right angle because of the converse of the Pythagorean theorem. 6 squared plus 8 squared equals 10 squared. 6 squared is 36, 8 squared is 64, 10 squared is 100, and 100 equals 100. This is indicative of right triangles by the converse of the Pythagorean theorem. By the converse of the Pythagorean theorem. Sorry about the handwriting. Kind of getting there. Number 37. Number 37, you are making a kite, and they might literally mean the kite shape kite thing, like from trapezoids and all that. I need to figure out how much binding to buy. You need the binding for the perimeter of the kite. So we need binding here, 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 and here. The binding comes in packages of 2 yards. How many packages should you buy? Interesting that an interesting problem. So number 37, let's kind of draw this out. I'm going to draw, how do I do this? I'm going to do like a triangle. It's not required. I could just draw a kite much more easily. But I'm going to draw 2 triangles, and I'm going to flip one over. Give me a second. Because I don't think my software has a kite shape. If I flip this over and kind of line them up like this, then you kind of have the appearance of something that could be a kite, right? Hopefully that kind of makes sense. And here, I'm going to draw a line representing a diagonal of the kite. Yes, it's called a diagonal. Kites' diagonals are perpendicular. So this is perpendicular. These are bisected right here into this. They even show you that. If this is 12 inches, then so is this 12 inches. They probably should have gone without telling you that. See if you still remembered. And then 15 inches right here. And 20 inches down here. Excuse me. Now, all of this is all about finding these lengths. Whatever this is the same. Whatever this is the same. I'll call them Z's. I don't know why. 12, 15, and an unknown. In a... it's not a 3, 4, 5 triangle. Not a special... It's not a special triangle here. So for x, we can do 12 squared plus 15 squared, and that equals some x squared. That's 144 plus 225. And that gives you 369. And x is the square root of 369. Now, I'm going to, I guess, round it. So 369 square root. I get 19.2-ish. I'll put 19.21 inches. So there's x. 2 of those, and I'm going to probably store this number in my calculator here that I have. I'm going to double 2 of those and get some other number there. So if that's x, then 2x's is 38.42. That's fine as far as rounding goes. That's good. The next set, this is z. I got 12 and 20 here. Also not something in a Pythagorean triple as far as I can tell. So let's figure out those ones. We'll do 12 squared plus 20 squared equals z squared. Z squared. Yeah, definitely not Pythagorean triple. So z squared is 544, and the square root of that, it's less than 24, not by much. 544 square root, 23.323. Z is about 23.32 inches. Let's double that one as well. I'm just getting ahead of it when it comes to perimeter. Two z's is 46.65 inches. Now you might be wondering, Mr. Robinson, you doubled 23.32 and you got 46.65. Where did the 5 come from? Why isn't it 46.64? Because I'm not doubling 23.32. I'm doubling 38. Not 38. I'm doubling. I can't find what my number was. Whatever the square root of 544 is. 544 square root. I'm doubling 23.323807579. I'm doubling whatever that bigger number is without rounding. So I want to make sure that I have that. That's kind of why I also wanted to keep these as far as their actual numbers were. So I'm going to try that for the other one. 2 times the square root of 369. And in total for both of these, the perimeter of this kite, I'm just going to say adding them up, is around 85.07 inches. 85.07 inches. Now, that's the perimeter of the kite, rounded. Okay. What I'm going to do, it says the binding comes in packages of 2 yards. Now, if this is more proportion talk, 2 yards is, sorry, 1 yard is 36 feet. 36 inches is 3 feet, which is 36 inches. 2 yards is 72 inches. Now, this is 85.07 inches. I need to buy a whole pack of binding, but I only would cover 72 of the 85.07 inches. So I have to buy a whole another pack. So 85.07 is greater than 72. There's more to it than that. It's the multiples of 72. 72, 144, 216. But 85 is the next step up. So you need to buy 2 packages. You can't read that. How many should you buy? You should buy. Will you use all the binding in the second package? No. You're barely going to get into it, but you need it. You should buy 2 packages of binding. Okay, let's keep moving forward. That was kind of a longer problem. Number 38, proving a theorem. Use the Pythagorean theorem to prove the hypotenuse leg congruence theorem. Yeah, the hypotenuse leg congruence theorem is all about, it's an angle side case, but you're not allowed to have angle side, if that makes sense, right? You have angle side with another triangle, right? The whole idea of hypotenuse leg is 2 triangles that are congruent, but you're allowed to use hypotenuse leg in this angle side case. But normally you can't. Why is a right triangle an exception? Because in Pythagorean theorem, you could find out that this squared plus this squared is this squared, this third thing here, and these would be congruent, which leads you to be able to either use side, or side angle side, like that, side angle side. So it says use the theorem to prove this theorem here, and I think I'm kind of doing that right here. I know I'm not doing the full bit, but using Pythagorean theorem, the third sets of sides would then be congruent to each other. I don't really know what I need to do for this proof to make this so, to kind of make that statement. Let me copy these things down. And kind of do something with this, okay? I don't know if they want a 2-column proof, but I can kind of make one up. So, statements, reasons. And then give me 1 second. I have to fix something outside of here. I'm back. Okay. Where was I? So I think what I want to do for this set of problems is, because they don't give us letters for anything, so I guess I make up my own. I'll call this like A and C and like X and Z or something like that. So I don't know if this is a perfect way to do the proof. I kind of stated what you got to do here anyway. So given A equals X and C equals Z, given. And then I'll add a B here and a Y. A squared plus, A squared plus B squared, geez, what is that? A squared plus B squared equals C squared, and X squared plus Y squared equals Z squared. This is Pythagorean Theorem. I'll just put PT. Now I'm going to get B and Y by themselves, or the squareds on both sides of the equation here. B squared is C squared minus A squared. And then Z squared, no, not Z squared, Y squared is Z squared minus X squared. This is the subtraction property of equality. I'll just put subtraction. And then these, because A is X and C is Z, I can substitute them into there, for example. I can say something like Y squared is C is Z, right? So C squared minus A squared, and then X is that one. So that's a substitution. So now B squared and Y squared both equal the same thing, so they can equal each other. B squared equals Y squared. That's the transitive property. And then therefore B equals Y. By taking the square root of both sides, I don't know if that's called the square root property of equality, so I'll just say take the square root of both sides. Like the subtraction property of equality, you can take the square root of one side as you can the other. If B equals Y, then that means that these two triangles are congruent. I can either say side, 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 or side, angle, side, and I get an option of one or the other. Triangles are congruent, because see, here's the thing, I didn't come up with side length things. Or angle. See, I should have done something like this, like A, B, C, like that. But I just went for the lengths because they didn't really give me enough. But it's Pythagorean Theorem that gets me there. But the triangles are now congruent either by side, side, side congruence theorem or side, angle, side congruence theorem. And they save us time from doing all that by calling that HL, and that's what makes that allowed. It's a good question. It's a good question. And because normally angle, side, side is not a case that we can use that on, but we can here. Okay, number 39, proving a theorem. Prove the converse of the Pythagorean theorem. Why don't they prove the Pythagorean theorem itself? Hint, draw a triangle ABC with side lengths AB and C, where C is the length of the longest side. Then draw a right triangle with side lengths AB and X, where X is the length of the hypotenuse. Compare lengths C and X. Draw a triangle ABC, where C is the longest side. I'll make it kind of look like a right triangle as well. Maybe not perfect. Totally not perfect. Absolutely not perfect. But so A, B, and C. Then draw a right triangle with side lengths AB and X, where X... Oh, I shouldn't make the right angle marking. A, B, C. Then draw a right triangle with side lengths A, B, and X, where X is the length of the hypotenuse. Compare lengths C and Z. So I have one that is for sure a right triangle in A, B, and X, and the other one in A, B, and C, where this thing is. Prove it. Maybe we can use the thingy. What's that called? Indirect proof? Is it indirect proof? Like the first let's assume thing? I think that's what they're called. I think that makes sense to these things that we can say that. So like first, let's assume that A squared plus B squared, oh boy, does not equal C squared, right? It can be greater than or less than. I think this is the kind of thing I want to say. Right? Does not equal C squared. Let me kind of copy and paste the squared thing. C squared, there we go. Let's first assume that's not true. And this is what, temporarily? Let's temporarily assume that. A squared plus B squared does not equal C squared. If so, then it's not a right triangle. I'm trying to think if I need to say that yet. If so, then it wouldn't be a right triangle. I'm trying to think. I might not have to actually say that part, but it wouldn't be a right triangle. However, because A, B, and X do make a right triangle, then A squared plus B squared equals X squared. B squared equals X squared is true because of the Pythagorean theorem. Since C equals X, wait, compare C and X. By the transitive property of equality, X is the square. No, wait, hold on a second. X. I'm trying to think if I should be squaring that C there as well. No, not by transitive property. It would be impossible for C squared to then not equal A squared plus B squared. I don't know if I'm writing this best. To not then equal A squared plus B squared. I feel like I'm doing it right, but I don't know. If it must, then like A, B, and X, then A, B, and C must be a right triangle. I'm getting the idea, I believe, and I hope that that kind of works enough. I don't know if if indirect proof is the way to go there, but I think that kind of works for me. You could have probably done something else, but I think that's pretty fun and pretty good. All right, let's go to number 40. We're almost done. I think 4 more questions. Consider 2 positive integers, m and n, where m is greater than n. Do the following expressions produce a Pythagorean triple? If yes, prove your answer. If no, give a counterexample. Consider 2 positive integers for n. Okay. 40. I have m greater than n. Positive integers. Do the following expressions produce a Pythagorean triple? Okay. So 2mn, m squared minus n squared, and m squared plus n squared. Are these a Pythagorean triple? If so, then that would be cool. I wasn't aware how this thing would work. If m is greater than n, then this would give all large things. M squared plus n squared would be bigger than m squared minus n squared always. Is 2mn always greater than m squared? Excuse me, is m squared plus n squared always greater than 2mn? In these cases, yes, because they have to be positive integers. If the smallest n could ever be is 1. That means the smallest m could ever be is 2. And 2 times 2 times 1 is 4, whereas 2 squared plus 1 squared is 5. That means this will always be the biggest. Always biggest here. Because quadratics will only just make it bigger. Always biggest. Now, why does this matter? They're asking whether this produces a Pythagorean triple. To produce a Pythagorean triple, they're already positive numbers. To produce a Pythagorean triple, we have to see that this squared plus this squared, because these would be the leg lengths, and this would be the hypotenuse here, equals this squared. Let's see. Do they equal each other? Without moving things to other sides of the equation, here I get 2mn quantity squared, which is 4m squared n squared. And here I get to square this part. That is m to the 4th minus 2m squared n squared plus n to the 4th. This is expansion of a binomial into a perfect square trinomial. And I'm going to do the same thing here. M to the 4th plus 2m squared n squared plus n to the 4th. That's me taking my Algebra 1 stuff, or my Algebra 1, my Integrated Math 2 fall semester stuff, that we had done before. Now, 4m squared n squared minus 2m squared n squared is positive 2m squared n squared. So here I get m to the fourth minus 2m squared n squared plus n to the fourth. And on this side, I have the same thing. M to the fourth plus 2m squared n squared plus n to the fourth. Because they equal each other, the answer is yes, they do perform. They do perform. They produce a Pythagorean triple. If no, give a counterexample. I don't have one. I don't have one. They both equal the same thing on both sides. If they equal the same thing on both sides, then you have something in the form of a right triangle because we use Pythagorean theorem for that. Okay. Number 41. Your friend claims 72 and 75 cannot be part of a Pythagorean triple because 72 squared plus 79 squared does not equal a positive integer squared. Is your friend correct? Explain your reasoning. Yeah. I want to make sure that's true and then make sure that I'm reading that question right. But otherwise, yeah. 72 squared plus 75 squared is 10,809. Take the square root and you get 103.9. Yeah. Yeah. Your friend is correct. A Pythagorean triple requires, I guess triple's not a proper proper noun, requires that all three values of the triangle are integers. So yeah, your friend's correct. All right, number 42, proving a theorem. Copy and complete the proof of the Pythagorean inequalities theorem when c squared is less than a squared plus b squared. Given in triangle ABC, we never proved the Pythagorean theorem, did we? Oh, prove the Pythagorean. Oh, yeah, I don't think we ever proved it. I figured this would have proved. Maybe it's on a different page. Maybe it's way outside of the section. I didn't look at the page. But copy and complete the proof of the Pythagorean inequalities theorem right here. Oh, we got to do this whole thing. Okay, I totally missed that. All right, let me leave that on the screen and let me copy and paste this part and see if, I'm glad we don't have to like build the whole thing. We actually just need to justify reasons. Let's hope I can do that. So we'll have the top part there. Give me a moment while I get this one set up. I didn't realize this was all part of the same problem. So there we go. Let's try this out. Number one, in triangle this is a lot. In triangle ABC, c squared is less than a squared plus b squared. Wait, what are we proving? Oh, it's an acute triangle. Where c is the length of the longest side. PQR has side lengths a, b, and x. Where did he did something like that? See, this is what I should have done with the other one. I should have given them other names of the letters on the vertices. Where x is the length of the hypotenuse and angle r is a right angle. So, oh, listen, we're going to do the same thing that we did before on the other one, only I didn't give them names here, which is fine. However, we're going to do it for an acute triangle instead of a right triangle. So, this is a given. Whoops. A squared plus b squared equals x squared is the Pythagorean theorem. Given that you have a right triangle there, PQR, triangle PQR is side lengths here where x is the length of the hypotenuse. Hypotenuse is going to say that. C squared is less than x squared. I guess that's transitive property of equality because you're taking the a squared plus b squared is less than c squared. And c squared is either that or it's a substitution. But something that's less than that, I'm just going to call it transitive property of equality. I don't know if that's exactly fully right, but something that's less than something else that's equal to something else means that other thing is also less than that something. If 3 is less than 5 and 5 equals 5, that doesn't work. If 3 is less than x and x equals 5, then 3 is less than 5. C is less than x, you take the square root of both sides. That's what they say here. I guess it's not a property of equality, but you take the square root. Measure of angle r equals 90. That's the definition of a right angle. They already said angle r is a right angle. So definition of right angle. Measure of angle c is less than measure of angle r, converse of the hinge theorem. If you recall, the hinge theorem states, because here we can have something like, oh, we have them here. We have something like, oh, I forgot about the drawing right here. if converse of the hinge theorem. If x is greater than c, then the side opposite x is going to be greater than the side, or the angle opposite side x is going to be greater than the angle opposite side c, given that a and b are the same lengths on both of these guys. And that's what they're showing on by the converse of the hinge theorem. Measure of angle c is less than 90 also looks like a bit of transitive property of equality. If r is 90 and c is less than r, then c is less than 90. 90 is taking place of r. That's transitive property of equality, at least more so. I believe that one more. I believe the other one would have been as well. And then c is an acute angle. It's the definition of an acute angle. Acute angles are angles less than 90. ABC is an acute triangle. It's the definition of an acute triangle. An acute triangle has only acute angles. So I think that's how you fill that one out. That looks pretty good. Okay, and the last question was what? Number 43. Prove the Pythagorean inequalities theorem when c squared is greater than a squared plus b squared. If it's the same as this, look back at exercise. Yeah, if it's the same as 42, I'm going to take everything that 42 has literally, and I'm going to basically just change very little. So I was going to say again, I'm surprised they don't have Pythagorean theorem on here as a proof, but it must be on some other page where we're not doing it. It's a pretty nice proof. Let's just change this to a greater than. C is the side length, the longest side, right angle. I think basically all these change like that. Greater than, greater than, greater than, greater than, obtuse, and obtuse. So I think that all works out. So in triangle ABC, this is greater than a squared plus b squared. It's the longest side. It has side lengths here. R is a right angle given. I think I can pretty much write the same things here. This is Pythagorean theorem. This is transitive property of equality. Now c is greater than x when we take the square root of both sides, the square root thing. Definition of a right angle. Here, converse of the hinge theorem, this will be greater than it now that c is greater than x in this way. C is greater than 90, once again, transitive property of equality. C is now an obtuse angle by definition of obtuse angle instead of acute angle. And an obtuse triangle is a triangle with one obtuse angle in it, definition of obtuse triangle. Okay. That's it. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this section 9.1. We are going to continue. Just seeing guys stand in the background. I don't know what they're doing. But we're going to continue in section 9.2, etc. in the future. So look out for that one. Check out the description section down below if you need to find any more stuff from me. I have a calculator handy for all this stuff. It might be in use. Thank you. Take care. I'll see you in the next one.